Hello everyone, welcome back to the another session in design and analysis of algorithms. Today we'll be going to talk about optimal binary search tree. So this topic you'll find in third unit as topic number 9. So this video will be going to cover what is binary search tree and what is optimal binary search tree, and we are very much aware that every searching operation will be having successful case, unsuccessful case. What do you mean by successful case? The element what I would like to search in the tree is found. So when the element is founded, then it is successful. If you did not find any element what you are looking for, then it is unsuccessful search. So we'll be going to know successful search comparisons, unsuccessful search comparisons, and we'll take an example. Then we will calculate the cost of the binary search tree. Then we'll look at how dynamic programming can be applied on optimal binary search tree. We'll solve a problem by taking some example from previous question paper. So I'm sure that I cannot cover all these content in single video, but we'll do one thing. We'll make up to this into one video and this into the other video. Whoever is watching this video, I suggest to watch the next video also for the better understanding of this topic. Now let's get started. So what is binary search tree? Now a binary tree is a tree where it will have at most 2 children. That is called as binary tree. Now that means if I construct any tree, if I considered any tree, now can I call this as a binary tree? Yes, it is a binary tree. Can I call this as a binary tree? Yes, it is a binary tree. Can I call this as a binary tree? No. Why the reason? Because it is having 3 children. So I told you that binary tree will be having at most 2 children, not more than that. It can be called as a tree, but it cannot be called as a binary tree. So the point is what? Binary tree always will have at most 2 children, either 0 or 1 or 2. Now what is binary search tree? Binary search tree, I am calling these elements with the name of keys. Now what is binary search tree? The binary search tree, the keys are arranged such that for any node, if you take, all the smaller keys are on the left hand side. All the larger keys are right hand side. Now, when you given with some set of elements, what we will be doing is, we will be making one element as root element. So this is my root element. If I pick the other element from the list of elements, I'll be going to compare the second element with the root element. If I found that is lesser, then I will be putting that element under left subtree. If the element what I'm going to pick from the list is seems to be greater from root element, then I'll keep that element in the right hand side, because it gives an advantage for searching. And this is called as binary search tree. Okay, now I want to search. Let's assume that I wanted to search 30. How to search 30 element from this tree? Start from the root. So root element is what? 40. Root element is 40. That means root double is equal to 30. Now root is what? 40. 40 double equal to 30. It is not true. Then we'll write the other condition. The other condition is what? Key element, whatsoever element I wanted to search, whether it is lesser from root. If it is less than from root, my searching operation, binary search operation, will be at left hand side. If it is not, that means if key is not less than from root, we'll write other condition, and now binary searching operation will be right hand side. Now let's take this example and understand. So 30 is my key element what I wanted to search. So root double equal to 30 element is not match with this. So obviously condition fail and we'll come down to the other condition to check. Key less than root. Now 40 and 30. 30 and 40. 30 is lesser from 40. So you will be having a probability that the element will be at left hand side. Now we'll start searching left hand side. Come. So left hand side, left subtree is there. Now 30 will get compared with the root element of left subtree. Now it is what? Greater than from this root. That means element may have at right hand side of this 20. So we'll come down. Now it will becomes a root node, right? Maybe you cannot see any children here, but as far as the tree is considered, it is also root when you come down to here. Now again 30 double equal to 20, 30 double equal to 30. Match found, then element is found. For searching 30, how many comparisons we have done? How many comparisons? We compared with this element, one comparison, and we also compare with this element, two comparisons, and finally when you come down from 20 to 30, again you compare over here, right? So how many comparisons? The maximum comparisons for any element is equal to the level of it. So in the case of 30, how many comparisons we made? 3 comparisons. Now, let us take the other example. Now, I wanted to search this 50. Now, for this time, my second case is 50 is my searching element. Then, how many comparisons it also required? We'll be going to compare with the root element. Now, this time not 30, it is 50. Compare with the root element. Match not found. So, we'll go to the other condition. 50 less than 40. 50 is greater, so it is also not true. We'll come here. Key greater than root. Yes, it is true. Now it will get, we'll be going to print the search is found. So how many comparisons for this time? 1 and 2 and 3. So for this 50 also maximum number of comparisons are 3. If you take any element, the maximum number of comparisons are 3. Now, let's suppose I wanted to search this 40 only. How many number of comparisons? 1. For 20, how many number of comparisons? We will start with this root node. If it is not, then we'll come to the second condition. Now, this time it will be matched. So, how many comparisons? It is required 2. For 10, it is 3. For 30, also 3. For 60, it is 2. For 50, it is 3. For 70, it is 3. So, what I am trying to say is, the maximum number of comparisons are exactly equal to the level of the tree. The level of the tree. Now, what is this level of the tree? Level of the tree is, this is what the first level, and this is what the second level, and this is what the third level. So, maximum number of comparisons always will be equals to level of the tree. Now, it is what successful case. In both the cases, in 30 case and in 50 case, we found element in the tree. That means it is successful search. Now, let's see unsuccessful search. That means I wanted to find out the element which is 9. So, 9 actually is not presented in the tree, but I would like to search 9. Then, how my searching operation will be done? So, I'm just comparing with the 40. I found 9 is less than from 40. So, as far as the condition is considered, my element will be at left hand side, will come at left hand side. Now, again 20 is found greater and 9 found it is lesser. Then we will search at left hand side of this 20. Now, we'll come to this 10. Now, here 10 seems to be greater than from 9. Then 9 probability will be here. Correct? So, why it will be here? 9 is lesser than of 10. 9 is actually not presented. If it is presented, it would be under 10. So, this is what? Minus infinity to 9. The probability 10 after the 10, if you wanted to take any element, that will be probably from minus infinity to 9. Now, in the same case, now I am taking this. Right hand side of 10 will be what? Any guess? It is 10. Now, obviously, 10 right hand side should be greater than of 10. So, that means 11 to 19. Because 20 already the root of that subtree. Right? So, now, I am just drawing this square boxes. Circle boxes are to represent the keys what are available in the list. Square nodes or square symbols I am representing for unsuccessful elements, the element which is not founded, but there will be a probability. If it is in the case that you wanted to take unsuccessful search case, the probability in the tree is I am calculating. So 9 is not found because I have reached till the end of a binary search tree, and key element is not found. So if a element is not found, then the search is called as unsuccessful search. So we need to know the amount of comparisons that we are doing, and that amount of comparison is nothing but the cost of searching in a binary search tree. Now, more thing, unsuccessful nodes are representing with dummy nodes. I told you this dummy nodes. Square boxes are representing dummy nodes, and these nodes are what? Unsuccessful nodes. Now, so I am taking unsuccessful nodes, these. So total how many elements you have? 1, 2, 3, 4, 5, 6, 7. Total 7 elements, right? Your n value for this tree, is 7. N is equal to 7. And that means what? Keys availability. I'll just make it is fresh to understand. The total number of nodes, which are n is equal to 7. Correct? That means successful nodes. Successful nodes in this binary tree is equal to 7. Now what about unsuccessful nodes? That means square nodes. Square nodes of a tree is equal to n plus 1. You can draw here. 10 can have 2 dummy nodes. 30 can have 2 dummy nodes. 50 can have 2 dummy nodes. 70 can have 2 dummy nodes. So calculated, it will be n plus 1. So total it is 8. Now, from this what we have to understand is successful search, unsuccessful search, successful number of comparisons, unsuccessful number of comparisons, always it will be n plus 1. 10 you found over here. If you have any element in the next level, that will be here, right? So basically the probability of successful nodes will get started with the 1. And for unsuccessful, we'll start with the 0. Right? Now we'll take an example and we'll just move to understand how many comparisons we'll take, the maximum number of comparisons. That gives the cost of the tree. The reason why I'm calculating maximum number of comparison is, that is what cost of the tree. So now we'll take